Good morning. Today is our last session, so lecture number 36 will be about body plots and exam 3 return. So this is 4/26, Friday, body plot. So the classes ends today, it's the last class day. Then the exam will be Friday, final exam. And starts at 8 a.m. So I encourage you to go to Canvas. There is exam sample with their answer, and also you will see the formula sheets. The formula sheet, I think, has 4 pages. This formula sheet will be provided to you, and you are allowed to have a note card as well. So yeah, 5 by 3. Yes.
What's the test then?
The test?
Yeah. It's going to be here?
Yes, it's going to be here.
Excellent.
Then it's cumulative, including everything we're covered. From number 1 until 36. Okay? Any questions about the final? Okay, let's finish the body plots. So basically with body plots, we will discuss more the approximated body plots. We didn't have enough time to cover the exact, but that's what we will discuss, the approximated body plots. So we can summarize it basically by trying to convert the transfer function into one of the 4 following scenarios. The first following scenario to get a 0. So we will try to make the transfer function written as 1 plus j omega over omega c. Omega c can be a constant, which is we call it sometimes the threshold frequency or whatever, cutoff frequency, something like that. So we will basically convert, substitutes every s by j omega, then make it divided by a constant, omega c. How we will do that, we'll talk later, but now let's see what's the effect of the 0. The 0 will make a slope 20 dB per decade. And that slope is activated at omega c. Which means before omega c it will be 0, at omega c it will be activated. That was in the magnitude. While regarding to the angle or the phase shift, because as we discussed last lecture, the body plot can be for the angle and for the magnitude, because any complex quantity can be magnitude and angle. So for the angle, basically it will make at omega c, the angle will be positive 45 degrees. So decay before omega c will be 0, then increasing. Decay after omega c will reach 90%, then stop. Okay, what does this mean? Let's do first, or let's do both actually. I'm going to make, here's a plot. Omega. Here's omega. The first one, phi of omega, which is the angle, or the second one. The first one, a of omega in dB, which is the magnitude. The first one in the top, the magnitude. The second one is the angle, the omega. Let's assume omega c equal 10. So we can say this is 1, here is 10, 10 power 2, 10 power 3. Then the same thing, here is 0.1, then here 0.1, 1, 10, 10 power 2, 10 power 3. Why we are using this axis? Because it's algorithm 10 in base 10. That's why we are using this. We will not use 1, 2, 3, 0.1, or maybe 0.01, 0.1, 1, 10, 100, 10 power 3, 10 power 4, 10 power 5, etc. So since omega c equal 10, let's assume we have only a 0. So what's happening is at omega c, here is omega c, for the magnitude it will start with a slope 20 dB per decade. Before that it is 0. So the slope here, 20 dB per decade. This means at 10 power 2, it will be 20 dB. At 10 power 3, 20 plus 20, 40. That's what's happening. It is the slope every decay. When we move from 10 power 1 to 10 power 2, it will be 20. 10 power 2, 10 power 3, the old 1 plus 20, and so on. That's how it looks like. Okay? Understand? Then how about the angle? The angle, omega c, at omega c is omega c, the angle will be negative 45. And it will start the decay before omega c. The decay before 10 is 1. So it will start from 1 to be negative 45. Then the next decay at 10 power 2, it will be 90 degrees. Before 1, it will be 0. After that, it will remain constant. It will remain at 90 degrees. That's the difference. So in the angle, at 10, it will be negative 45. Decay before 10, it will start increasing. Decay after 10, it will stop. And it will stop at 90 degrees. Okay, understood? That's the effect of the zero. Now the other thing, how about the pole? When we have a pole. The pole means whenever you have a pole, try to make it as 1 plus j omega over omega c. So the pole is the opposite effect of the zero. So basically, what's happening, the slope will be negative 20 dB per decay instead of positive. Then the angle, and activated at omega c, of course. Then the angle at omega c, it will be negative 45 degrees. Decay before omega c start increasing. Stop at decay after omega c, which will be 90 degrees. In other words, negative 90 degrees. In other words, at 0.1 omega c, it will be 0. Omega c will be negative 45 degrees. 10 omega c will be negative 90 degrees. Then stop here. It will remain constant. Okay? Let's do an example. Assuming omega c, assume omega c equal to, and let's do the plots. Now the plot will be negative. Why it is negative? Because it's pole. Here is omega, here is a of omega lima. Then the next one, here is omega, here is phi of omega. Okay? So let's put the decays, 0.1, 1, 10, use whatever you need. Maybe you don't need 0.1. So you can evaluate based on where is omega c. Omega c is 10, so it's enough to say 1, 10, 10 power 2, 10 power 3. If you can use 0.1, that's fine. Here the same 0.1, 1. Try to be consistent with this magnitude and angle, 10 power 2, 10 power 3. So again, omega c is here. Omega c is here. So according to the analysis, before omega c in the magnitude it will be 0. After omega c it will be with the slope negative 20 dB per decay. So at 10 power 2 will be negative 20 dB. 10 power 3 negative 20 and another negative 20. This will make it negative 40. Okay? Does this make sense? Again, the slope negative 20 dB per decay. Whenever you move from omega c to 10 omega c, it will be negative 20. To 100 omega c, negative 40, and so on. It's like a linear relationship, but when you use the log or the algorithm. How about the other thing, which is the angle? Omega c, at omega c will be negative 45. The decay after omega c, it will be negative 90 degrees. So decay before omega c, 1, to move like this, and here remains constant at negative 90 degrees. Okay? Does this make sense? It's actually the mirror of the zero, or the opposite of the zero. Any questions? Let's move to step number 3. What's step number 3? Now, we say about pole and zero if we have 1 plus j omega over omega c. How about if we don't have the 1? If we have only this one, this scenario. This is, we call it, this is still 0, but with no one, where there's no imaginary axis, or when there's no real parts. So what's happening? What's the effect of it? So it is linear with slope 20 dB. There is no activation, activated or it's linear, no activation, but it is 0 intersection, the 0 intersection at omega equal omega c. How about the angle? 90 degrees phase always. There is no activation at omega c. What does this mean? Let me do the plots. Assume omega c equal 10. So here is the magnitude, omega dB, and here is the angle. And let's assume omega c here as 10, here is 10. So what's happening? It will be like this. Continue from negative infinity to infinity, but the intersection at omega c. So how about if we are, for example, we have 0.1, here is 10, or 2. So it is the slope, again, negative 20 dB, actually positive, per decay. So at 10 power 2, this will be 20 dB. Here, this is also like negative 20 dB, something like that. It is linear relationship. How about the omega? It will be, the angle will be remain constant at 90 degrees. Okay? Does this make sense? So the difference, look at the difference between 3 and 1. 3 continue from negative infinity to infinity. While 1, look at the magnitude, start from the cutoff frequency, from omega c. Before omega c, everything was zeros, or clipped from that. So you will start from omega c. After omega c, number 1 and 3 will be the same, but before omega c, there will be something. Then look at the angle. Before activating omega c, or the cutoff frequency, the angle was 0. Then after that, it starts increasing step by step to 90 degrees. While that one, it is going directly to 90 degrees. The difference between number 1 and number 3 is if you add 1 plus j omega over omega c, you will be number 1. If you remove 1 plus j omega over omega c, then you will be number 3. Okay, how we can get this result? We can see it by an example, but we have 3 scenarios. Now the fourth scenario, which is up pole, 1 over j omega over omega c, which is the opposite of that one. So this scenario, since it's a pole, the same way that I mentioned here, linear, but the slope will be negative. Linear with slope negative 20 dB per decay. Okay, intersection 0. Intersection at omega c. Then what's happening to the phase shift? Negative 90 degrees phase. Okay? Negative 90 degrees phase. So, assuming omega c equal to 10, what's happening? Here is omega. Here is omega. This is A of omega, dB, and here is phi of omega. So let's assume omega c here, 10, 10. Here is 1, 10 power 2, 10 power 2. Okay. So what's happening? It is decaying, which is going down. Intersection at omega c. The intersection at omega c. Going down. With negative 20 dB per decay. So at this one, at 1, it will be 20 dB. At 10 power 2, it will be negative 20. Okay? How about the angle? The angle, it's easy. It will be negative 90 degrees direct. Okay? Does this make sense? Any question?
these four scenarios, we will use them in an example. Now, I want you to understand this. Then let's see how we can apply it in an example. Basically, you have the transfer function. Or, you might have a circuit, and you can use your Laplace transformation to convert from time domain to S domain to find the transfer function for the output voltage, output current, whatever you need. Then after that, you will have the overall transfer function. You already know this, how to deal with this in the second exam. Then the next step is to draw the Bode plots. Let's assume after you solve a certain circuit, you get x of s 1000 s over s plus 100. Let's assume this is the transfer function after we did this. How we get the transfer function, we know. You can go back to the recordings and see. So the first thing, which is what we need to do is to substitute s by j omega. So we're going to draw the Bode plots. And when we mean draw the Bode plots, we mean both magnitude and angle. Okay. Now, how we can do it? So basically, x of omega will be 1000 omega j omega divided by j omega plus 1. Okay? Now, it is not on the standard format that what we know in the four cases. 1 plus j omega over something, right? That's what it's supposed to be. It's still not 1 over j omega because those constants are not 1. We need to make, or our idea is to make this constant 1. How to make this constant 1? Multiply by 1 over 100, divide by 1 over 100. Again, the key is to make the constant 1. So what will happen? It will make it 1000 divided by 100 will make it 10 times j omega divided by j omega over 100 plus 1. Okay? Then we can let the 10 out of it. Why? Because what we have learned before, j omega over omega c, not 100 times j omega. So we can split it into 3 terms. So basically, we can say this can be written as 10 times j omega over 1 plus j omega over 100. Okay? So far, we have 3 terms. This is term 1, term 2, term 3. So in order to find in dB, x of omega in dB, it is 20 log of 10 plus 20 log of j omega plus 20 log of 1 over 1 plus j omega over 1. Okay? So again, this is term 1, this is term 2, this is term 3. Now look at term 2. Term 2, j omega inside the algorithm, which is j omega. Term 1, 1 over j omega, 1 over 1 plus j omega over 100. So term 3, we already know it, right? We already know the procedure, basically. The cutoff frequency here is 1. Term 2, it is j omega, which is j omega over 1. That's how we calculate it. So the cutoff frequency here is 1. How about 10? Okay, we've never did it. We have never talked about 10. What do we do with the constant? 20 log 10. Log 10 is 1. 20 log 1, 20. Right? I'm sorry, 20 times 1. Because log 10 is 1. 20 times 1, 20. So this yields to be 20 plus j omega. That one will make it in dB plus 1 over 1 plus j omega over 100. So this is 20 dB. Now how we do this? Let's do each term alone. So let's do the term 1 first. So here's term 1, which is 20 dB. Term 1. How about term 2? Term 2, which is the cutoff frequency equal 1, then here equal 1. And it is, we said it's j omega. Since j omega it will be linear, and it will start from negative infinity to infinity. So here it's at 1, and omega or point 1 will be negative 20 dB. At 1, it will be 20 dB. And so on, it is increasing. At 10, 40 dB. At 100, 60 dB. Okay? So that's increasing, it is 20 dB per dB. How about the third term? All of them here is omega, omega, omega. Third term, term 3. So the cutoff frequency is 100. So here is 100. Before 100, it is 0. After 100, it will be with slope negative 20 dB. Okay? So how is the scenario will look like? Basically, the sum, or x of omega in dB, the magnitude, we need to put all of the frequencies. So here we have 100, then we have 10, 1, then 0.1. Let's start in what's happening before 0.1. Before 0.1, it is here, or at 0.1 we can say, let's start from 0.1. At 0.1, it was negative 20 dB. While, look, and you can think about it. 0.1 here we need to sum term 1 plus term 2 plus term 3. Term 1 plus term 2 plus term 3. So 20 plus, at 0.1 it was negative 20, which will make it 0. Then plus 0 will make it 0. So at 0.1, it will be actually 0. Then, at 1, what's happening? At 1, we have 20 dB and 20, so which will make it 40. Let's see, at point, here is 1, this is point 1.
Yeah, I think you went from point 1, skipped 1, and then...
Yeah, so it is... Here should be activated at 1. Okay, I get it. So here it should be 1, here. This is 1, I skipped 1. The zero intersection here was at 1. Then at 20 dB, we expand at 20 resist. So here is 1, and here is 10. So at 10, it will be 20 dB. At 100, will be 40 dB. Oh. So let's start from, again, from 1. From point 1. From point 1, it is negative 20. Then here we have 20, we'll make it 0. So the intersection will be at point 1. How about 1? At 1, it is 0. Here is 0. Here is 20. 0 plus 0 plus 20. 20. So it will increase linear. Which will make it close to 20. Now, how about at 10? 10, here it is 20, and here is 20. This is 0. So which will make it 20 plus 20? 40, correct? So it will be 40. Now between 10 to 100, between 10 to 100, before reaching, when we reach 100, exactly 100, this is 40, 20, and 0 will make it 60, correct? So it will make it 60. So it will keep going until reaching 60. Let me make it nice. So here's 40, 60. So it will reach up to 60. Then, at 100, what's happening after 100? This is 20. Here is the slope, negative 20. Or here's the slope, slope 0, slope 20, slope negative 120. So what will happen to the slope? 0, which will make it constant. So it will maintain at 40, at 60. Because the slope equal to 0 plus 20 minus 20, which will make it 0. Then it will remain only at 60. So it will increase from negative infinity. At point 1 will reach 0, 120. Then at 10 will reach 40, 160, then maintain at 60. Okay, does this make sense? Now, how about the phase? Okay, how about the phase plots? Phase plots, remember we have 3 terms. So the 10th term, it is only a real number, then angle 0, no problem. Okay? Yes?
So would that function be like a high-pass amplifier?
Yes. Okay. Now this was number 1. Term 2, which is 1 plus j omega, or it's not, it's j omega, which is j omega over 1. So basically, this causes 90 degrees phase. With no, it's not like a cutoff frequency. Why? It's just j omega, it's not 1 plus j omega. If it's 1 plus j omega, it will be different. It is only j omega, that's term 2. So what's happening, it will be 90 degrees like this. This is term 2. Term 1 is negligible with angle 0, it's real number. Now, third thing, which is 1 plus j omega over 1. So here, since there is plus 1, this will matter, the cutoff frequency will matter. So what's happening here? At omega, it will be 45 degrees, which is at 100. At 0.1 omega c, it is 0 degrees. At 10 omega c, which will make it 90 degrees and stuff. So what's happening is, it will look like this, and omega c, which is 100, then we have before omega c, which is 10, after omega c, 10 power 3. So we can say this 10 power 3. Here is omega c. Then we can say it starts to be negative 4. Here it is, it's 4, I think. So I need to write 1 over I this. I missed it's a 4, so there's a negative sign, negative sign. Okay? Because it's a 4. 1 over j. That's the j. So what will happen? Let me do it. Yeah, it's a 4. So what's happening? It is starting from 0 to be negative 45. Oh, no, this one. The 0 intersection and 10. Omega c now, it will reach negative 45 degrees. Then at here it will reach negative 90 degrees. So that's how the front will lie. Then we will maintain at negative 90. Okay? This is term 3. Now, to do the shifts, the angle, we need to term 1 plus 2 plus 3. Term 2, 90 degrees. 1 is 0. Then term 3 is plus 90 degrees. So the sum, here is, I need to plot the phi omega. So phi of omega, this is term 1 plus term 2 plus term 3. I can write the diagonals here first, like we have point 1, 1, 10, 10 power 2, 10 power 3, and so on. So at before 10, this one was 0. This one is 90 degrees, the other one was 0. So it will be 90 degrees. Before 10, it will be positive with 90 degrees. Until reaching the point. So it is 90 degrees. Now at 10, what's going on? At 10, this is 90, maintain constants. And the other thing which is decay. So it will be at omega c negative 45. Negative 45 plus 90 will make it 45, right? So this will be slow going down. So at omega c will be 45 degrees. Okay? Then how about at 10 power 3? At 10 power 3, this reaches 90, negative 90. And here we have positive 90, negative 90, and positive 90. 0. So if we go 0, then after 10 power 3 will be 0 because negative 90 plus 90 will make it 0. Then this is the first point. Okay. Does this make sense? Yes.
What are like the practical applications of like designing a phase shift?
This is most likely you will use it in control system. So in control, there's a transfer function, and the zeros and poles are really matters. So basically, sometimes you need to move the poles. You know, the poles, they are sometimes stable system, unstable system. We said bounded input, bounded output system. One is the pole's location at the left-hand side, right? So if the pole's at the right-hand side, this will lead to unstable system. So our target when we design the controllers, either the PID controller or the state feedback controller, whatever we do, we will try to move the location of the poles from right-hand side to be in left-hand side. So this will lead to be have a stable system. The other thing, as you will discuss later in the control system, how fast the system, how the response is fast, is based on how's the location of the poles. Roughly, as an example, the farthest point away in the left-hand side, if you go more beyond the left-hand side, will make the system super fast. If you go closer to the imaginary axis, the system response will be slow. Then you will have some challenges. Okay, I need to make the system so fast, but I have a physical constraints. I cannot make it that fast. I cannot make it super fast. So at the same time, I don't want to make it too slow. So you need to get the optimal performance. So we see how is the poles and the zeros. When we change them, the magnetic change will be affected, the angle will be affected. That's one thing. Other ways, you can use it in communications when you design the filters. Low-pass filters, band-pass filters. So there are several applications on how to use this. So you will use this later a lot. And most likely we have a MATLAB plot, so the MATLAB will do the whole job. Okay? So you just put the pole zeros, then you can play with it. Then you can design the optimal or the best location for the pole and the zero based on the body plots to maintain a stable system fast enough to good response. Any other question? Okay, so any question about this example? This is example that was combinative and supported the answer. Yes?
So for the magnitude plot,
Yes.
like the first, that one will equal to 20, like a constant 20.
Yes, 20. But you mean after 100? That's the constant?
I thought like the constant.
Yeah, the constant, comes from the 10 here. So when we do the Bode plot or do algorithm, it will be 20 log 10 plus 20 log j omega plus 20 log 1 over 1 plus j omega over 1.
So my question is, when you actually did the plot though, you had it reach 0. But if there's a constant 20 all the time, I don't understand how to reach 0.
Yeah, when you do the addition, subtraction, it will not reach 0 because, I mean, term 1 every time is 20. Okay? Then when you do, which part, which interval?
For the, I don't, okay, I see one part of it, but never mind. I just misunderstood the last one.
If we still need something, we can take the right side. Any other question? Okay. Now I'm going to give you another example. Assume we have this. This is important. L equal 1 Henry. R equal 1 ohms. C equal 0.1 farad. And this is plus minus V out of S. Assume we have this, and we need to find the transfer function. So, question number 1, find the transfer function. Question number 2, draw the Bode plots. Okay? Let's start with number 1. Number 1, we need to find the transfer function. So A of V of S, which is the transfer function of the voltage, V out of S over Vn of S. Okay? How to find V out over Vn? Basically, you can imagine there is a voltage division. So I would say in the circuit analysis, there is a voltage division. Vn equals to, actually V out equals to Vn, this is voltage division, times the impedance SC over 1 plus SC plus 1 over SC, the impedance 1 over SC, 1 over SC plus R plus SL. Do you remember this voltage division? Voltage division. V out equal Vn times ZL over the sum of these. Do you recall this? Do you know? Then that's what we did. So once we've done with this, we try to make the transfer function as nice as possible. So this yields when we make V out over Vn, this will make the closed loop gain to be 1 over SC divided by 1 over SC plus R plus SL. Then you can multiply each side by SC over SC. Okay, we are almost running out of time, so please bear with me. 1 divided by L C S squared plus R C S plus 1. Now substitute L C equal 0.1. LC equal 0.1, RC equal 1.1. This yields the transfer function to be as 1 over 0.1 S squared plus 1.1 S plus 1. Okay? Then, when we deal with this, we can say, make it more nice, 10 over S squared plus 11S plus 10. If you try to convert this to poles, 10 over S plus 1 times S plus 10. This is AV of S. This is the transfer function. So question number 1 done. Question number 2, we need to find the Bode plots. To find the Bode plots, basically, we need to convert everything to substitute S equal to J omega. So this will yield to be AV of omega to be 10 over S plus 1 J omega plus 1, then J omega plus 3. Okay? Our target is to make it like 1 plus J omega over omega C, or 1 over 1 plus J omega over omega C. What limits our ability is the existence of the 10. We need to make it as 1. So what I'm going to do, which is 1 over 10 times 1 over 10 for both sides. So this yields the closed loop to be 1 over 1 plus J omega times 1 plus j omega over t. Okay, does this make sense? Okay. Then I can split it to be as 1 over 1 plus j omega, this is term 1, then term 2, 1 over 1 plus j omega over t. So we can do term 1 first, and term 2 second. Term 1, here is term 2. So, with term 1, I know we are running out of time, so if you need to leave, you can leave. I'm sorry about this, I'm getting late. But I'll try to finish it up, and the recording, well, I'll keep recording, so if you need to leave, you're still able to see the recording. So 1 plus j omega. So what's happening? Term 1, the cutoff frequency at 1. Term 2, the cutoff frequency at 2. So in order to do the magnitude of term 1, and here's the magnitude for term 2, it is at, here is, let's see, point 1, let's say here is 1, 10, 10.2, then the same thing here, point 1, 1, 1, 10, 10. So all of them are false. This means it will be negative. So what's happening? The term 1 at omega will be negative 20 dB. Term 2 negative 20 dB. All of them are false. Then term 2 is activated at 10. So here it will be negative 20 dB. Then the remaining are zeros, remaining are zeros. Now my target is to sum, because AV of omega in dB, which is the sum, term 1 plus term 2. Then what's happening? It is here, point 1, here is 1, 10, 2. All of them will be negative. So it's activated at 1. Before 1, everything was zeros. After 1, it will be with slope negative 20 dB. So here is slope, here is negative 20 dB. Then the slope here, negative 20 dB. Now at 10, what's happening? The slope will be different. Will be make it negative 20. Negative 20 dB per decay plus negative 20 will make the slope negative 40. Negative 20 plus negative 20 will make it negative 40. So we'll make it like this. Slope negative 40 dB. Therefore, this yields at 10 power 2, it will be instead of negative 20 plus negative 20, negative 40, it will be negative 60 because it's okay? Does this make sense? Now the last thing, which is the phase. How to plot the phase. Term 1. To plot the phase. Basically, I would say the first term, which is at omega c equal 1. At point 1, omega c 0. At omega c will make it negative 45, 10 omega c will make it negative 90 degrees. So how we can draw it, basically, this is the plots, here is term 1, then it is omega c, which is here 1, so we have 0.1, we have 1, 10 power 2, then at term 1, at point 1, we'll make it, it will start to be decreasing with a negative 45. Then at 10, will be negative 90 degrees. Okay, after that will remain constants, negative 90 degrees. How about term 2? Term 2, omega c equal to 10. So at omega c equal 1, increasing omega c 1 point omega c equal to 0, omega c will be 45 degrees, 10 omega c will be 90 degrees. So for term 2, here's omega, 10 power 2, 10, 1.1. Then, we will start at 0.1 of the 10, which is at 1. Will be, then we'll move to negative 40, then negative 90. This is term 2. Now the last thing, which is to draw the overall, which is here, T of omega. Here is 0.1, 1, 10, 10 power 2. Here is omega, and now we are doing the sum. Term 1 plus term 2. Now before 0.1, everything was 0. So before 0.1, everything was 0. At between 0.1 and 0.2, it will go to negative 45. 0.1 to 1, negative 45. Then between 1 to 10, negative 45, and there is negative 45 on one side, another negative 45 on one side, which is negative 90. Negative 90 minus 45. Also is negative 90 minus 45 will be negative 135, right? So it will move slowly more. Negative 135. Now at 10, will be here negative 90. Yeah, that's what we said on. At 10 power 2, there will be negative 90, negative 90, negative 180. So it will be on the same slope here. That's negative 180. Okay, so this is the end of the example. Any questions?